Good morning. Here we are once again. It's the physics video lecture, Physics 105B video lecture 13. A couple of great things. We're going to wrap up the small oscillations by completing that masses on a chain problem that I started last time. And then we're moving into gravity of extended objects, which is a great theory as well. Good, so we'll start with the masses on a chain. Chain of masses. That takes a little more time than we had available last time. So we'll set this up again. Instead of just one or two or three, we have a whole large number n of these things. Make a nicer picture. They're just in one dimension, a mass on a spring, and you just continue on for quite a while. The number n is supposed to be very large. There's no friction. And we want to write down the Lagrangian kinetic energy, potential energy, Lagrangian equations of motion, and then we'll work with those. So this goes on, and we have the same spring constant, same mass, just repeated. And there's a separation distance that's going to come into play later between their equilibrium positions. This is the x-axis. And what I do is I pick out three of these. I have J plus 1, J minus 1. That's enough. And now let's write down the kinetic energy. T is equal to, we had this last time, half mxi dot squared. Potential energy is going to be, again, a sum of these half k delta x squareds. So we have k xj plus 1 minus xj, the quantity squared. And here j is going from 1 to n minus 1. And now the end objects here, we have a half k x1 squared, and we have a half k xn squared over here, and that's the entire kinetic potential energy. And as we see, we're going to ignore, and just probably ignore the endpoints anyway, because we're just going to work with this set right here to get the general Euler-Lagrange equation. So we have L is t minus u, but in particular we can say that the time derivative of dl dx nu dot dl dx nu equals 0. That's the Euler-Lagrange equation. We can recognize that here we're only differentiating the kinetic energy, so it's actually d over dt, d kinetic energy dx nu dot, and over here it's just the potential d u dx nu, and since we have a minus u there, this would be plus. This would be a plus sign equals 0, or we could say equals minus du dx nu. And that's a fun way to look at it, because of course this is just Newton's law, derivative of this expression minus the gradient, okay, minus the derivative of the potential energy. Okay, so we're going to be on the right track there. And working directly underneath here, we have dt, so clearly mx nu second derivative on the left side. That's from this equals minus, and then potential energy with respect to x sub nu, and I had pointed out last time, and I'll do it again, we're going to have 1/2 k x nu plus, we have two expressions. X nu plus 1 minus x nu, and 1/2 k x nu minus x nu minus 1. Point is that that one particular coordinate that we're looking at shows up in two of these adjacent expressions. So yeah, and these were squared. So we got the minus sign outside already. We have k x nu plus 1 minus x nu. And then the inner derivative we're taking right there gives us a minus 1. And then we have k x nu minus x nu minus 1. And this is what we're going to clear up, and we'll end up where we were last time. We have minus times minus is plus, so what we end up with is a k here, and we have x nu plus 1, and then the x nu is going to have a minus sign both times from here, and then the double minus sign there. So minus sign minus 2 x nu plus x nu minus 1. So let's put a box around here. There's our equation of motion for some arbitrarily chosen mass on this chain here somewhere in the middle. And mass times acceleration, the force depends on the relative positions, or the position of itself and the other two as well. So that makes complete sense. Coupled oscillations. Now what's interesting is that instead of set this up and solve it, we want to turn it into a partial differential equation. So next, we're going to interpret x sub nu, we'll call it x sub nu of t as the displacement u of x sub nu and t. Let's write that out a little cleaner. And t. And once more, we'll do it. There we go. So what do we mean by that? What we're going to do is associate the displacement of this numbered particle here as a displacement at that location. Okay, so we're interpreting the displacement here as a location on the number line. So let's just go ahead and draw this. So this is now our x-axis, and we have the same thing we had before. X nu plus 1, x nu minus 1. Okay, but what we have is at this location the displacement of the mass. So we should put a couple words there. U is displacement of the particle located at x sub nu. And we're going to try to get a continuum description of this. So what we're going to try to do is place these masses, smear them out along the entire line eventually. So what we first have to do is interpret this thing right here. And there's x nu plus 1, x nu minus 1. So this difference equation, remember we have that separation L. This difference equation can be interpreted as, and yeah, just this part here is what we have to write down. So we have x nu plus 1, that's u of x nu plus L, okay, because that's the position here plus L, and I'll leave out the time for the moment, minus u of x nu, that's one of those, and then we're going to put parentheses around there and subtract off u of x nu, that's the second one, minus u of x nu minus L. Okay. So you can see we still have that expression there. This is a difference, so what we're going to do is square bracket the whole thing, multiply by L, and divide by L. What could go wrong? Multiply by L, divide by L. And now it looks like we have difference quotients for derivatives. And right underneath here, I'll say what we have. We have L, open bracket, and now we have, give it a little more room. This would be a partial with respect to x, located where? Here's my red pen. X of nu plus L, x of nu. So we could think of that as a partial derivative for x of nu plus L over 2. That would be right in the middle of those two. Right? Located right there. So that du dx of x of nu plus L over 2. And this one over here would be minus du dx x of nu minus L over 2. Right, so we have this thing here and that location there. So those are the partial derivatives across here. Okay. And close bracket. And now I'm going to work on this expression right here by multiplying and dividing by L again. Like that. And this is again a derivative. So this is a difference quotient, and because nu plus L over 2 minus nu minus L over 2, it's actually centered right at x of nu. Okay. So this being a difference quotient, I'm going to write it right underneath here. And make sure the essential stuff stays up on the board. That's fine. Okay, so that expression in the red box up there is going to look like the following. So one final line here, what apparently we have is L squared D squared U EX squared, and this was x of nu and t, namely the location, right there on the x of nu is one there. So that's what we have found. That was my right side of the red box, and of course it would be multiplied by k. So now we have, now m x new second derivative equals k L squared d squared u dx squared. Oh, this one we had already taken care of, had we not? Yeah. M d squared u dt squared. Shoulda, woulda, coulda, right there. We're interpreting that x as u, so the second derivative was the partial second derivative with respect to time. Okay. So we've got that. Now the question is, how do we take the limit as L goes to 0? That appears to be a bit of a problem, because we want to make the spacing between those masses go to 0 as we redistribute the mass uniformly along the chain there. So we have to take L goes to 0. And there's an interesting argument there. It's going to work. So next, d squared u dt squared equals k L squared over m d squared u dx squared. You know what I could say is this. Right here, it's still an approximation because we just had difference quotients. Okay, here's an approximation. We want to make it an equal sign by taking limit L goes to 0. And in fact, we can take the limit as L goes to 0 if we imagine distributing the masses uniformly. I'm going to go ahead and draw this one more time. I don't have to draw any squiggly springs anymore. So we have masses, we have spring constants K, and we have a separation L on each of these. So here's what we're going to do. It turns out that this limit as L goes to 0 remains constant. Because limit KL squared over M as L goes to 0 is constant. And the proof of that is kind of interesting, okay? Here's what we do. So we're going to prove this thing. Proof of that idea right there. The thing is, we're going to let M go to M over 2 as we redistribute the masses evenly. Or distributed. So what we're going to do is, I'll say M go to 2 times M over 2. We're going to cut these masses in half and put them all at the midpoints. Okay. Okay. Then L is going to L over 2. Okay. And K is going to 2K, because when you take a spring and cut it in half, an ideal spring cut in half actually has twice the spring constant. That can be demonstrated in a number of ways, but we showed that in our problem with the 2 masses and 3 springs, where the effective spring constant for the normal mode was 2K prime, right? K plus 2K prime. That came from the center spring. So that's a natural property of these things. And so what you end up having is this. You have K L squared over M goes to 2K L over 2 squared M over 2. Okay, and all the 2's cancel, and you're left with KL squared over M. So if we just step by step imagine distributing those masses, and then we repeat the process, cut them in half again, and distribute them on these quarter lengths ad infinitum, that's how we're taking this limit KL squared over M going to 0. Yeah, so make sure you understand that. And there we go. We have an equation, and this is actually the wave equation. So we've derived for the motion, for longitudinal motions along this chain of masses, we've derived the wave equation. That's how the disturbance, you could say, propagates according to the wave equation. Go ahead and erase this. Yeah, make sure you understand this as well. This construction, we started with what's in the square bracket, and we ended up with the second derivative, the second partial derivative. And it's a very robust expression too, because of these midpoints where we took these, where we evaluated these things. This difference right across the midpoints, perfect. And people who do numerical work know all about this, okay? That's how you do second derivatives on discrete lattice. Okay. Good. So let's say a little bit more about the wave equation. We'll end this section here. Conceivably, if we have time at the end of the semester, we get to fluid mechanics and a wave equation in fluids as well. But we'll see how far we get. We have other things to do as well. Good, so we have the one-dimensional wave equation d squared u dt squared equals v squared d squared u dx squared. Now this v squared is just a number, KL squared over M. So for homework, just to make sure you see this, check the dimensions here. Right? Dimensional analysis has to give you length over time squared. Length over time squared for this thing here. So now we have our wave equation. And you've seen wave equations before. Where have you seen them before? In optics class? Other physics classes. So we've just derived it under these circumstances here from little masses on a chain. I'll just say a couple things briefly about the wave equation. A solution to the wave equation can be of the following form. You can say u of x and t equals u, should I use u? I'll use the same function of x plus or minus v times t. So in that case, you just have a function that's a function of one variable. And if you had just u of x, you could take, for example, a little pulse centered at the origin. Okay. And if u of x is a pulse centered at the origin, then if you take the minus sign, u of x minus vt, as t grows, this original origin is shifted to the right. Okay, so it's a traveling wave solution. And the plus sign here, this pulse would be shifting to the left. You go ahead, you go into this differential equation, you get d squared u dt squared equals, if you take those time derivatives, you get u double prime of the argument times plus or minus v, the quantity squared. Okay. And of course, that's just v squared times second derivative with respect to x, which is just u double prime. So yes, a pulse of this type is a solution of the wave equation. Now, one thing has been lost here, and that is that we could just as well have some really dramatic pulse, okay, that would satisfy this wave equation. But this actually came from the theory of small oscillations, and a dramatic pulse like this would completely violate the small oscillations assumption, right, that the displacements were very small. So in fact, just note that this pulse here would satisfy the wave equation just trivially, but real, physical solutions, let's talk about it that way, have to have a pulse that represents very small displacements. So physical solutions are for small displacements. So the assumption always is that the amplitude is much smaller than the extent. Later on, if you're talking about wavelengths, then you'd say the amplitude is much less than the wavelength. That kind of thing. So yeah, there we go. I don't think we're going to study the wave equation in any great detail. Maybe a little bit more if we get to it again at the end of the semester in 3 dimensions. But yeah, we'll leave it at that. There are also sinusoidal solutions, and then you have wavelengths, wave numbers, and frequencies. That's not present here right now. You can easily build that in and show that your sinusoidal traveling solutions satisfy a wave equation as well. But for right now, just these pulses. So this would have been more of a physical pulse, okay, a small amplitude. This is an unphysical one. They both satisfy this. Okay. So, yeah, we're doing time-wise. Oh, great. So this new topic, gravitation with extended objects, is going to bring a bunch of our skills and formulas into play. So we started, and we ended last semester and then discussed this semester the many particle systems of many particles. And then we went to Lagrangian mechanics and did systems with many degrees of freedom. And we also did Taylor expansions in order to deal with those many variable Taylor expansions. That's all going to be rehearsed and repeated here. So yeah, the next entire chapter here, we're going to call this gravitational theory of extended objects. Gravitation with extended bodies. Now we've been making use of a theorem, namely that a spherical body acts just like a point mass. A spherical mass distribution acts just like a point mass distribution, and we're going to actually prove that, one of the first things we do here. And then the gravitation with extended bodies, that's really a bit of field theory. We'll do some approximations of the type you're going to do in electricity and magnetism as well. Good to see it more than once. Okay. So gravitation with extended bodies. Here's the way we're going to look at it. Suppose we have, there's a point mass M, and that'll be at location R. And our extended body is a collection of point masses. Maybe they're somehow rigidly connected. So they're all contained within some volume, and that volume has a surface. So we have volume V, surface of that volume, we use this symbol. This del V refers to the surface that bounds that volume. And all of these are some jth particles. So we have m sub j, r sub j, j equals 1 to n. So the force on this particle, I'll put that under here, the force on m is due to all of these, one more vector here, this is r minus r sub j. Remember we did with the two-body problem, we set these up here. Now we're just going to have a whole collection of these. I think we've seen this before. So we have F is equal to, and remember it's gravitation, so it's the sum of m sub j g, j equals 1 to m. So I'm thinking of this m as being outside of this volume there, m sub j g, and let's go ahead and write this out, r minus r sub j divided by r minus r sub j vector magnitude q. Okay, so we got a little bookkeeping here right now. And because we're being attracted to the jth particle, we have to put a minus sign in front of here. Okay. And there we go, that's the expression. We can also express this as m times g. F equals m times g, where this g is now the gravitational field. G equals the gravitational field at point R, the gravitational field right here. And all that means is I'm going to divide out m. So we would say that G at point R is equal to minus G sum over m sub I R minus R sub J vector divided by R minus R sub J magnitude cubed. Okay, that's a lot of particles here. J equals 1 to n. I'm using J to tag those particles here. R is, this location, this particle here. And we're being attracted to all those particles. It's a gravitational attraction to every single one of them. Okay, the next thing now is I want to use Gauss's integral theorem to prove Gauss's law. Gauss's law that you know from electrostatics, possibly. But I'm just going to do a calculation using Gauss's integral theorem. And I may leave a couple steps for you guys to complete. So let's see how this goes. So with that example, with this expression right here, we're going to form the flux integral. So you've seen electric field and flux, but you can do the same thing with gravity. And there's our volume there. So let's just say we had this integral, the boundary of the volume, I'll say it's a closed integral. And we have G dot n hat, where n hat's the surface normal, dA is the surface, infinitesimal surface element. So n hat dA would be the So it would be the directed surface element. That's the outer surface normal. I'm going to want to start this on the left side of the board, so let's do it over here. So we're going to have G dot n hat dA. So the first thing we do is plug all of that in there, and we have, since it's a finite collection of particles, we have minus G sum over J equals 1 to n m sub J. We can do that too, but now we have to have this integral boundary of V r minus r sub J r minus r sub J cubed dot n hat d area. Maybe something I should have noted, this r over r cubed, that is 1 over r squared law times a unit vector. Okay, so if you don't remember that, write it down. This is 1 over r minus r sub j squared, which is the magnitude of Newton's law of gravity, and then the unit vector gives you the direction. So that's this difference divided by the magnitude cubed. Just so you remember that, it's a vector, that's a magnitude. And what we want to do is use the divergence theorem. So according to the divergence theorem, we would have minus G sum over m sub j, j equals 1 to n, integral over the entire volume, the divergence of r minus r sub j, r minus r sub j, cubed, I'll write d volume. Okay, that's the divergence theorem. The divergence theorem has about 4 names behind it. Gauss, of course, there, but every nationality wanted to have their share of that theorem. Okay, look it up sometime. So here we go. Now, this is something I wanted to, I can either do it for you or I could leave it on the homework. Yeah, there's some good practice to be had right here. Namely, what we do is we find, surprisingly, this equals 0 for r not equal to r sub j equals 0. Now, that's a calculation everybody should do, but the question is, if that equals 0, then how can that be? There's no expectation of it to be 0. This entire thing equal to 0. Well, the key is it equals 0. If you take the divergence of this, it's going to vanish, but it's undefined when r equals r sub j, okay? Because you can't just plug into 0. So it's 0 everywhere else. I'm going to put homework there. And I'll show you how to set that up. This expression here would just be it would be the sum d dx sub nu equals 1 to 3. Remember, the divergence is the derivative with respect to x of the x component of the vector is a vector plus y plus z component, right? So it would be, the x component of this thing would be x sub nu minus x sub j nu. Okay. This is the one we're differentiating with respect, and this would be the r minus r sub j cubed. So if you do this differentiation carefully, you're going to find that this here is true. I guess since I got started on it, I'll do it right under here. So we're going to do it as a product rule type thing. So first we're differentiating with respect to x sub nu and holding that constant. So we have the sum over equals 1 to 3 of 1 over r minus r sub j cubed. And then we're going to have a sum x nu minus x j nu. And we're differentiating with respect to x sub nu in this expression here. Well, first of all, it's minus 3 times what we have down here to the fourth. Okay. And now what is the inner derivative? The inner derivative is basically an vector r over magnitude r type of expression. So since we're just doing a single component and then summing them up, what we end up with here is x nu minus x j nu over r minus r sub j cubed. Okay. You know, this is a homework regardless of whether I do it or not. You guys have to look at this and really make sure you understand it. Okay? It's just part of vector calculus. And I'll just point out what's going to happen here. I've got minus 3, you can pull that out. This x nu minus x j nu is squared, and when I sum that up from nu equals 1 to 3, I'm just getting r minus rj magnitude squared. Okay. So in the numerator, I'm getting this magnitude squared. That was wrong. That was supposed to be a first power. Okay. Getting it squared in the numerator and to the fourth power in the denominator. So that's 1 over, that's the fifth. No, squared over fourth. Gotta catch your mistakes in real time. Minus 3, this was the third, so this is the fourth. Okay, now we got it. So we have 4 plus 1 is 5. 2 powers here, so it's going to be this expression here with a minus 3 in front of it. But this expression is being added 3 times. Okay, so this is 3 times r minus rj cubed minus 3 times the same thing equals 0. When r is not equal to rj. Man, this argument's taking so long. Are we going to run over? No, we won't. Okay, so we did that calculation. Here's what happens. We go backwards. We go backwards with this. Go ahead and erase this right here. We're going to keep that picture. So, since we have that 0, except where those things are, we can, so I'm continuing my expression up there, continuing my equal sign. What I now have is g sum over m sub j, j equals 1 to n. I have this divergence theorem. Here we go. Let's just write this down. I'm rewriting what I have there. Divergence of r minus r sub j, r minus r sub j cubed d volume. Except I'm no longer integrating over this entire volume. It's 0 everywhere except at those points, so I'm going to call this b sub epsilon of r sub j. And that b sub epsilon of r sub j is just a little ball of radius epsilon, a little sphere, radius epsilon, around r sub j. Ball of radius epsilon centered on r sub j. Okay. And now that I have those little balls of radius epsilon, I can go backwards with my Gauss's theorem, divergence theorem, 1 to n. So by going backwards, I'm going to have to erase this thing here. I now have r minus, leave the room, r minus r sub j, r minus r sub j cubed. That's a vector divided by magnitudes, dotted into n hat. But the n hat itself is r minus r sub j, r minus r sub j cubed. That's what n hat is. I'll circle it. Okay, that is n hat, because it's an outer surface normal at that little ball, and therefore that's d area. And I can squeeze the answer in here. It's minus g, sum over all the masses inside. And this integral here turns into epsilon squared over epsilon, wrong power again, first power, epsilon squared over epsilon to the 4th times 4 pi epsilon squared. So this thing equals, I'm just going to give us a 4 pi, because this whole integral is equal to epsilon squared, epsilon to the 4th times 4 pi epsilon squared. Only works with the 1 over r squared. So there's our answer, what we started with up there. I'm going to fill that in. Fill that in and declare victory. So what we have is this flux integral, g dot n hat d area around the boundary of a volume is equal to minus 4 pi, all the epsilons canceled, minus 4 pi g sum of all the masses. And these are all the masses enclosed in the sphere. Or not yet a sphere, we're going to get to the sphere. This is the sum of the enclosed masses. That's Gauss's law, and you know it with electrostatic fields, and here it is with gravity. Minus sign is important. Everything here is so far so good. Minus sign came from the attraction. Okay, so I'm going to put on homework is to, you'll have it in your notes, you've got it in your notes, fine, but I want you to write it out as a homework and make sure you understand all of these steps. Very nice calculation. Homework, so what should we say? Understand this calculation. So turn in this as a calculation. In particular, I want you to know this divergence calculation here. Understand how that came into play. And also, when I gave this argument with these epsilon balls, make sure you see what's going on right there as well. So, volume, this. R sub j. Volume, this was the boundary, right? That's why it was just a boundary of surface 4 pi epsilon squared. Okay, it's all here. Have a good look at it, and after you've taken your notes, go ahead and write it out and work on all these little aspects. Make sure you get it. You won't regret it. It's a good problem. And good, we're on our way. We'll work with this a little bit next time and keep going. Okay, good. See you guys next time.